Hello, everyone. We continue the study of Module 1. Today, we are going to do Lecture 3, which is about the motion planning. By now, we have already studied task planning and action planning. So then we move on to study motion planning. Before we enter the study of today's lecture, it is always good for us to have a quick review about the learning objective. So you understand the learning objective of this course is for you to become designer of a robot as a product. So as a designer, you must have these 4 basic questions in mind. Question number 1, who are the user? Question number 2, what are the needs of the user? Question number 3, what are your robot which could meet the need of your user or buyer? Question number 4, what are the solutions behind the design of your robot? And there are 2 scenarios for you to answer the first 2 questions. Scenario number 1 is the case in which you have a specific user. Therefore, you follow, okay, the guideline or the procedure or steps in the right part of this slide. And in order to come out the conceptual design, embodiment design, then you do the prototyping, optimization, etc. All right. The second scenario is the case in which you do not know any specific user, but you still want to design and produce a robot as a product. And once you reach the stage of marketing and the sales, you would like to sell your robot or sell your product to as many buyers as possible. All right. Then in this second situation, you must consider generalize the user and generalize the need from this user. Therefore, we choose manufacturing industry as an example in order to know the generalized need from generalized user. All right, so this is why lecture 1, lecture 2 are quite important, and even lecture 3, okay, of module 1 is also very important. Okay, and in general, module 1 basically is for you, okay, to understand, okay, the nature of a generalized user and the generalized need, okay. Then you will be able to understand this statement, okay, about the question of what is robot. Okay, one way to answer this question is to say robot is a motion provider, right? Then from this statement, immediately you understand what is the generalized need from generalized user. The answer is what? They need to have, their need is to have a motion provider. And since robot is a motion provider, therefore, they need your robot, they will buy your robot, etc. All right, so you keep this thinking in mind, then you will understand that, okay, the context, the background thinking for lecture 1, lecture 2, lecture 3, etc. Okay, once we reach lecture 4 and 5, then you will see our focus will be on the equation of the motion. All right, then immediately you understand, okay, robot is a motion provider. All right, okay, then for question 3, question 4, this slide give you the answer to question 3. And this slide gives you the answer to question 4. Okay, so by now you will see, okay, the module RoboMan. Okay, so actually we are doing the study about this module. Okay, subsequently you will be able to understand the module which is about the robot body and the module which is about the robot modeling in terms of kinematics, dynamics. And the last module is about the robot control. All right, so you will see, okay, these are 4 major modules which are present in the generic blueprint of any robot. All right. Then how to implement this blueprint? Then you need to have knowledge behind the design of the blueprint. All right. So I categorize all the relevant knowledge into these 4 modules. So this slide basically shows you the, okay, the knowledge, okay, behind each module. For example, now we are doing the study of module 1. Then we need to know the task planning, action planning, motion planning, path planning, trajectory planning, etc. Okay. So then for the study of a robot body, then we need to know, okay, robot system, robot brain, robot mechanism, robot actuator, robot sensor, etc. All right. So within this course, you are going to study all these topics which are categorized into these 4 modules. All right. Now we enter the study of lecture 3 of module 1. Okay, and the title is motion planning. Then first question you may have in mind is, what is the purpose of doing motion planning? All right, then this slide gives you the answer. Then from this diagram, immediately you understand, okay? From a job description, we need to, okay, come out the task description or identify the task, then describe the task, okay? Then with the task description as an input, we need to identify action and describe this action, okay? Then we have an action description as an output. Then we will enter motion planning module, okay? So the input will be action description, then output will be motion description, okay? And then the output from motion planning will be the input to path planning, okay? And you from this flow of knowledge, you understand our intention is to reach the level of technical detail which could be understood by robot, okay? Because today's robot have a difficulty to understand the description in the form of a human language. However, if we can decompose description in the form of a human language into the description in the form of an equation, then robot will feel comfortable to execute the equation and take action according to the knowledge of the equation. All right. So then, so you understand the intention of module 1 is to link, okay, the descriptive knowledge into technical knowledge in the form of an equation. All right, because robots are comfortable with input of the equation. Okay, if you just input a text to today's robot, then today's robot will not respond to the text, okay, at all. So, all right. Okay, then what are the motion that the robot can perform? Because motion planning will output motion description which could be performed by robot. Therefore, we must pay attention to the type of motion that the robot can perform, all right? So in general, robot can perform two types of motion. One is linear motion, and the second one is angular motion, okay? For linear motion, for example, we may have a description such as a move to linear position, move with a linear displacement, set linear speed to a specific value or to an upper limit, or set the linear acceleration to an upper limit, etc. Okay. Then for angular motion, the description could be rotate to an angular position, rotate with angular displacement, and set the upper limit to angular speed, and set the upper limit to angular acceleration. Okay. Then this slide, basically this video will show you, okay, the motion that the robot can perform. So you will see this is the linear motion. So this is the angular motion. So basically, okay, these are the two types of motion that the robot can perform. Then through the combination of these two basic type of motion, then robot eventually can perform all kinds of motion. So you see robot can undergo translation, rotation, or combined motion or complex motion. Okay. Actually, this video shows you the scenario of human assist motion planning by teaching. Just now you see the human operator. The human operator is teaching the robot about the motion to be performed. Just now you see there's a screen there, okay? Then the display inside the screen basically show you the program in the form of instruction or library function, all right? Okay. So, and this slide basically show you, okay, we can describe motion with this simple sentence, move to linear position, okay? So then you can relay this motion description to the mathematical expression. Okay, so basically we need to know what is the position vector, then move to this position vector. Okay, and here we have a simple example. Let's say we have equipment to record the motion performed by robot. Okay, then this is a motion graph, okay, recorded by the measurement instrument. Okay, now we ask you, okay, what is the position of the robot at the time when t equal to 18 seconds? Then from here you see at the 18 second, the position of the robot is at the 2 meters. So immediately you know the answer, all right? We can also have this description for linear motion, move with linear displacement, okay? Then mathematically, it means we must have a displacement vector, okay? Displacement vector is equal to position vector at the T2 minus position vector at the T1. So the difference gives us the displacement vector, all right? And this is just a small exercise for you to, okay, understand what is the displacement vector, okay? So the robot opens the cap at the location 10, 20, 30 cm, and place it at the location 30, negative 10, 10. Then what is the displacement of the cap? Okay, so final position minus initial position, the result will be the displacement vector. All right. We can also have this description or this motion description, which will set the upper limit of velocity. Okay. Then what is velocity? Velocity is the ratio, is or time rate of displacement, or the ratio between displacement vector and the duration in which the displacement occurs. All right. So this is the average speed or average velocity. If we compute the first order derivatives of position function, then we have the velocity function. All right. So we can set the upper limit to these two values. All right. And here just a small example for you to know how to calculate average velocity. Okay. So assume in the previous example, the robot accomplished the performance of this motion within 2 seconds. Okay. Then displacement vector divided by 2 will give you the average velocity. All right. We can also have this motion description, which will set the upper limit for acceleration. Okay. Then what is acceleration? Acceleration is a time rate change of a velocity. Okay. In other words, it is a ratio. It is equal to the ratio between variation in velocity and duration in which the variation occurs. Okay. So this gives you the average acceleration. If we compute the first order derivatives of a velocity function, then the result will be acceleration. All right. And here is just a simple example. Okay. In this scenario, the robot will kick off the ball. Okay. Assume the ball initially is at the rest. Then when the ball take off, it will reach this velocity of 1.5, 0.0, 0.2 meter per second. Okay. And this process occurs within 0.5 seconds. Then what will be the average acceleration of the ball during the kickoff phase? Okay. Then the answer will be the variation of a velocity divided by duration. Then you get this answer, okay, which is 3.0, 0.0, 0.4 meter per second square. All right. For angular motion, we have a similar description. Okay. For example, this is a motion description for the change of a position. Okay, so we can ask a robot to rotate to a specific angular position. So angular position is a rotated angle about the axis. So in this case, the robot will rotate about the z-axis. Okay, so then we have a theta t, which will measure the angular position of the upper body of this robot. Then for this vehicle, you see the z-axis is perpendicular to the screen. Okay, then theta is the angular position of this mobile robot about the z-axis. Okay, then for robotic arm, so here we may have many angular position. For this joint, we have this angular position. For this joint, we have this angular position. And then for this joint, we also have this angular position. All right. And this is just a simple exercise for you to know, okay, what will be the angular position of the leg, okay? So the leg's lower limb, so the answer will be theta 3. Then what is the angular position of the leg's upper limb, okay? So the answer will be theta 2, okay? So it's this angle, okay? All right. And then for this robotic arm, okay, so it's the same for every joint. There is okay, angular position. When the robotic arm move, so the angular position will change. Okay, if we compute the difference between angular position at the time t2 and angular position at the time t1, the result will be angular displacement. Therefore, we may have this type of motion description, which set the angular displacement. Okay. So here is just a simple example for you to understand. Okay, the meaning of angular displacement. Okay, so initially the arm is fully extended, so therefore this angle is equal to 0. Then this person rotate the lower limb of the arm in order to reach this position. Then you will see this angle is 90 degrees. Therefore, the angular displacement is 90 degrees. All right. We may also have a similar motion description, which will set the upper limit to angular speed or angular velocity. Okay. So for angular velocity, so we just need to compute the ratio between variation of angular position and the duration in which the variation occurs. Okay. So this gives you the average angular velocity. And if we compute the first order derivative of angular position function, then the result will be angular velocity time function. All right. And here is just a simple example, okay, for you to determine, okay, what will be the angular velocity of the second joint. So this is the first joint, this is the second one, okay. So initially, what is within the time interval, okay. So when time change from 3 to 6, because here we give you the position function of these 3 joint angles. So you see theta 3, theta 1, theta 2. So these are the motion graph, okay, for position. Okay. Now we want to know, okay, within this time interval, what will be the average angular velocity? Okay, so time interval is 3 to 6. Okay, so when t equal to 6, the position for theta 2, okay, theta 2 is here. So position for theta 2 is roughly about 11.5. It's between 10 and the 12. You see the degree, 10 degree, 12 degree. Okay, then this is roughly 11.5. When t equal to 3, the angular position is 0. Okay, so then you compute the ratio, then you get this answer. All right, so this is theta 2. Theta 2 is here. All right. Then for the setting of the value limit to acceleration, we can use this motion description. Okay, and average acceleration is equal to the ratio between variation of angular velocity and duration in which the variation occurs. All right, and if we compute the first order derivatives of angular velocity, the result will be angular acceleration. All right. And here we just show you the application. This is an equation similar to the linear momentum. Okay. So it's like a mass times v is equal to linear momentum. Okay. Then this is a moment of inertia of a mass, okay, when you rotate about the axis times angular velocity. So this is equal to the angular linear momentum. So in physics, you understand. So without the external force, the linear momentum of any rigid body is conserved. Okay, that means this one is equal to constant. So therefore, if you reduce the moment of inertia, then angular velocity will increase. Or if you increase moment of inertia, then angular velocity will reduce because this value will remain constant. All right. So this is the way for for people to change, okay, to control the angular velocity. For example, in this case, the I is very big, then omega I will be small. Okay, in this case, I will be small, then omega will be big. All right, so this is a physical phenomenon for us to understand about the change, okay, of angular velocity. All right. Then this is a simple exercise, okay. Let's say this robot threw a ball, okay, to a certain distance, okay. Then the process occur within 0.5 seconds, and initially the ball is at the rest. And when the ball exit from the hand of the robot, the ball will reach this velocity, this angular velocity. Then we ask you to determine what should be the angular acceleration acting, okay, or reached by the ball, okay. So we just compute the ratio between the variation of angular velocity and the duration in which this variation occurs, okay. Then we will get this simple answer, all right. Okay, so the previous slide basically help you to understand, okay, the motivation for us to do motion planning, and in particular, what is the purpose for us to do motion planning. And motion planning is a module which is a process or procedure which has an input, which has an output, okay, which has an internal process, etc. So now we look into the detail of the input to motion planning, and the output from motion planning, and the inner process of the motion planning, okay? So we start with the detail of the input to motion planning, okay? So the input to motion planning from this diagram, immediately you understand, okay? So the input should be action description, all right? And the action description is in the form of natural language or human language. Then in this case, immediately you understand, okay, it will be very tough for today's robot to understand description in the form of complex human language, all right? And then what should be the key information contained inside an action description? Okay, the answer will be these three key information. Information number one should be the outcome of action to be achieved. Information number two should be the space constraint. Information number three should be the time constraint. Okay, here I just show you example. For example, for action undertaken by robot's arm, then you will see this series of action: approach, grasp, turn, push, walk through. So approach the door, grasp the handler of the door, turn the handler of the door, push the door, okay, to make it open, so open the door, then walk through, okay. So these are the action involved in task 3, okay. So here is a task 3, okay. Then here for task 9, task 7, you will see the challenges to undertake biped walking. Then the action involved in task 7, task 9 include support by leg, carry by leg, push by leg, swing by leg. Since the robot has a 2 leg, then we must plan the pair of action by a pair of leg, okay? If the left leg undertake action of a support, then the right leg will undertake the action of a push. When the left leg will undertake the action of a carry, the right leg will undertake the action of a swing. When the left leg undertakes the action of a push, then the right leg will undertake the action of a support. When the left leg undertakes the action of a swing, then the right leg will undertake the action of a carry. Okay, then by repeating this sequence of pair of action, then the robot will achieve the normal biped walking behavior. All right. So then here I give you one more example from the manufacturing process. Okay, if let's say we have this task description as an input, then what will be the action sequence as output? And this is a drilling process. Okay, so the task is to make use of rotating drill or drill bit in order to create hole of a desired dimension on stationary workpiece. Okay. Then what should be the action sequence? Okay, so this is a possible version of answer to the question. Okay, so we may have this version of action sequence. First action is to hold drill bit onto spindle. So you see spindle is here. So it's just to attach, okay, the drill bit onto the spindle. Then rotate the drill bit. Okay, when the drill bit start to rotate, then we press the rotating drill bit against the workpiece. Okay, then apply force to move the rotating drill bit down into the workpiece. Okay, so this will be the action sequence. Okay, in order to achieve the execution of the task. All right. And here is another example from manufacturing industry. If let's say we give you this task description, then what should be action sequence, okay, which will lead to the accomplishment of this task. So this task is to make use of a filler metal, okay, and which is melted and distributed into the fairing surface of a two metal part in order to join or bond them together so as to form a permanent joint. Okay, so this is like a soldering, but in this case, what is the difference between welding and the soldering? For welding, we need to join two metal together, and these two metal eventually may subject to heavy external payload and a strong external force. Okay, but for soldering, the process is also to join two components together or two metal together, but normally these two components will not subject to heavy external payload or strong external force. Okay, so you see the difference. Normally, when we talk about the soldering, usually it refers to the soldering of electronic component, for example, PCB. We solder component onto the PCB, etc. All right. Then we could identify this version of action sequence. Okay. For example, action number one, to place two metal parts together to form a desired joint, and then to move the torch and the filler rod together along the fairing surface, okay, or the joint surface, okay, and also we need to apply the thermal heat, okay, so as to melt the filler rod and then deposit additional material inside the joint. All right, and after that, then we do a little bit of inspection about the quality of the solder, okay, or joint, okay. So these are the possible sequence of action, okay. So that's about the input. So you understand the input to motion planning, description of action in the form of human language. Then what should be the output from motion planning? So the output from motion planning will be description of a motion in the form of extended human language. Okay, so we have a natural language. Natural language means language used by laymen. All right, then natural language could be extended by mathematics, okay, or technical language. And the natural language could be extended by programming language with library function. All right, so therefore, you see we start to enter, okay, more detail towards technique side, okay, or technique description, all right? So then the output of the motion will be motion description in the form of a script language. Script language means what? Is a language which is very close to mathematics, okay? So you see commands are very close to programming instruction, programming language, okay? Then or library function. A library function for sure is a part of a programming language. Okay, therefore, so you see, once we reach this level of detail, okay, in technique, then robot will feel comfortable, okay, because robot can understand mathematics, can understand the library function, or just code the library function and execute library function. All right. So then this is the starting point for robot to gain autonomy. Okay. To gain the freedom to perform. Okay. The planning and the execution control autonomously. Okay. So you see, before motion planning, robot has a weakness in intelligence because of the challenge faced by the need to understand human language. Now we move toward the technique side, then robot will feel comfortable. Okay, all right. So this is the boundary which separate, okay, conventional robot and intelligent robot. Okay, so our research is to make robot to be able to handle, for example, action description, task description, etc. All right. Okay. So this will be the output from motion planning, and then how to describe. Here is already tell you we describe motion in the form of a script language, library function. Okay. Then I just repeat again just to reinforce your idea about the simplicity at this level or the detail towards the technique side, okay, in terms of motion description, okay. So we have two solutions. One is to use the script language to describe the motion to be performed by robot, okay. For example, the script language may include these commands such as move to, move with, rotate to, rotate with. You see, these commands are very close to human language, okay? Or robot will make use of a library function such as a move to, bracket with argument inside. Here I did not write the argument, so you are totally free to put in any kinds of argument. Move with, rotate to, rotate with, okay? Once we reach this point, immediately you understand robot design involve not only mechanic design, but also software design, okay? And in module 4, you will also understand that the design of a robot involve design of a motion control system, all right? So the keyword design is very important. And it is also very important for you to put into the mindset of a designer. Therefore, then you understand, I need to design mechanic system for robot. I need to design software system for robot. I need to design control system for robot. I need to design communication system for robot, etc. Okay, so once you have this mindset of a designer, then you will enjoy the study of this course because you can link the knowledge that you are going to study with the need of the design. All right. Okay. So here immediately you see. Okay. So what will be the focus of software design for robot? Then this slide shows you the answer. Okay. So the key focus. Okay. For the software design in robotics is to design script language or library function. All right, both of them will be used for motion description. All right, and then what should be inside the description of the motion? Okay, regardless whether you use script language or library function. Okay, so the input, when you call the library function or when you use the commands in script language, okay, so these commands, this library function must indicate at least these three pieces of information, okay, either implicitly or explicitly. Implicitly means I move from my current position. A robot move from its current position, and in order to reach final position. Okay, so initial position of the robot arm could be implicit information. Okay, so from current position, then go to a new destination position. Okay, all right. So at least the description of a motion must include, okay, information about the initial position, orientation, and the final position and the orientation, plus time and the space constraint. All right, so this is very important. All right, by default, you may say the space is totally free. Okay, so you can relax this one. By default, okay, it's empty space, totally free, no risk of a collision. But however, you must give the time constraint, John. Okay, okay, go from A to B within 1 second, 1 minute, 1 hour. Okay, so you must tell robot, otherwise he do not know. Okay, the robot do not know. Okay, what will be the time duration for them to perform the motion. All right. Okay. So here just show you example which demonstrate the motion which could be performed by robot. And for each movement, you will see the initial position orientation, final position orientation, and also there's a time constraint and the space constraint, right? Okay. And here is one more example. You see, for each movement, there's an initial position orientation, final position orientation, plus duration, time constraint, and also, of course, space constraint. The robot must, okay, take the disk from the right location and insert it into the right location. Okay, so all these are space constraints, right? Here is another example. So this video shows you the space constraints very critical. If the robot make a slight mistake, then it will damage the glass. So here you see robot could outperform human being in terms of motion execution. The reason is because a robot could perform precise motion. However, for human beings, we are not so skillful in performing accurate motion. All right, okay, let me continue. Here's another example which showing you locomotion or wheel is a locomotion. You see here, all these vehicles are actually mobile robot, high-speed mobile robot. All right. So then for biped walking, so you have seen this video before. Then how about snake slide motion? All right. And we may have a mobile robot which could move on water surface.
Vessels transporting passengers and cargo without any onboard crew might not be science fiction for long. Meet the Venus, an unmanned surface vessel, or USV, a 9-meter-long boat that explores the vast stretches of ocean autonomously. ST Electronics has launched its cutting-edge technology in Singapore waters, making it one of the first nations in Southeast Asia to build and deploy the USV.
There's a lot of potential in this need for this unmanned system. In 2008, actually we started our very first USV development, which is this boat itself, which I'm standing on. This is a 9-meter unmanned surface vessel that we first developed.
ST Electronics launched the first USV 7 years ago, when it was developed for military missions such as mine countermeasures and anti-submarine warfare. The technology that supports this craft is actually one that many people are accustomed to. The vessel's path is first charted out on a mobile device, which is able to determine its exact marine route, speed, and even behavior. Once its mission begins, the vessel uses its navigation sensors to build situation awareness and to identify potential obstacles.
We have a lot of sensors that are put in place to help the vessel localize where it is. At the same time, know where to go. We have software to control basically how a vessel guides itself from point A to point B. This is a navigation radar that transmits RF. Right? So if there's an object there, radio frequency waves can bounce off all these objects and be collected back at this sensor. So over the scans, you're able to estimate whether all these objects are stationary or moving.
In addition to that, the vessel is well equipped with auxiliary sensors in the form of cameras in the event that the radar misses any obstacles. Now that the USV is tested, it is up to the market to define its commercial viability.
For example, you can actually just make a ferry boat carry passengers that is unmanned. Just like your MRT, where you don't need a driver to drive the MRT.
If you're talking about ferrying people, I think a safety number on board is still important. With the technology today, maybe he's just there to assure all the passengers in the ferry that at least the ferry is not driving by itself. More from a psychological assurance kind of thing.
ST Electronics has signed a 3-year memorandum of understanding with the Maritime and Port Authority of Singapore. Part of this MOU would be to research and develop the regulatory framework supporting the commercialization of the USV technology.
I think it's important for the authority to actually put in place regulation how the unmanned vessel could be coexist with a manned vessel on the maritime environment.
The USV holds vast potential as a technology, not just in removing humans from dangerous military missions such as minesweeping, but also in freeing up manpower from routine tasks.
For example, like you have to do a watch keep on board the ship, physically using a binocular to actually do watch keeping. Whereas with all this technology, with all the artificial intelligence that you build into the system, you can actually do all this mundane work for the operator.
ST Electronics expects to complete the full-scale development of the Venus USV for military and paramilitary use by end 2017. Advancing the technology for commercial and passenger shipping purposes will be its next goal. Conventional sea travel as we know it is set for a wave of change.
All right, then how about the motion inside the water? So you see we may have a fish-like robot. All right, so if we change the media from water to air, then fish will become a bird. So you see we have a bird like robot. Okay, so you will see planning play a very, very important role because without the planning, there will be no control. Without the control, then robot cannot demonstrate motion behavior. All right, so planning always comes first before control. All right. Now we look at the process, how to transform action description into motion description. All right. So there are two ways for us to do motion planning or for robot to do motion planning. One is to leverage on human assistance. And the second one is to leverage on robots' intelligence. Okay, so if let's say we leverage on humans' assistance, then this should be quite easier. For example, any human being can understand this action description to pick up an object at a specific location. Okay, then immediately this person should be able to come out the motion sequence, such as move to point AC. AC is here. Then open gripper. Okay, to open the hand. Move to point GP is a grasping point. Okay, then close the gripper just to grasp the object. Then move back to point AC. So then this sequence of action will help the robot to accomplish this action of pick up an object from the incoming conveyor. Okay, then subsequently we can ask this robot to place the object inside the empty box. Okay, when this empty box is full, then shift this one, then activate the conveyor to shift out the box, which is fully filled up with product. Then bring in another empty box here. Then repeat this this task. Okay, at this station. All right. Here is one more example, which showing you how human operator could assist robot to do motion planning. Okay, so in this case, we ask the human operator to write the program in the form of a script language or script commands. You see, define point hash, define point A, open gripper, move to A, close gripper, move to C, move to D, move to B, open gripper, move to D, etc. Okay, so you see this is a program in the form of a script language. And here is a program in the form of a programming language with a library function. So you see, we define, okay, the variable vector hash, define vector A, vector B, vector C. These are the position vector, vector C, vector D. Open the hand, move to. You see, we supply this argument. The argument is the next destination. Okay, from the current position, go to next position. Okay, so then close the hand and move to position vector C, move to position vector D, move to position vector B, open the gripper, open the hand, then move back to position vector D. All right. So these two programs are provided by human operator. All right. And here's another example. This showing you the assembly task. Okay. So the human operator will tell the robot what is the initial state before the assembly, what is the final state after the assembly. Okay, so the description will be at the position, that means the part A is the position P1, part B at the position P2, part C at the position P3, part D at the position P4. Okay, then now we want part B is on top of a part A, and part C is on top of a part B, and also is the part C is at the left end of a part B. Part D is on top of a part B, and part D is on the right end of a part B. So this describes the final state of assembly. This is the initial state of assembly. Then the human operator can help the robot, okay, to come out this sequence of motion description in the form of programming language. Okay, you can say this is a program, or you can say this is a motion description in the form of a library function. All right, so they are the same. All right, so basically you see every instruction is about one motion. So you have a motion sequence. Okay, so the result, the nature of this piece of information refers to motion sequence. Okay, for example, open the hand, and define a new position vector. New position vector is the difference between these two vectors, okay? Position vector P2 minus the offset vector, okay? Then move to this new position vector, close the hand, then change this position vector again, which is difference between position vector P1 and this offset vector. Then move to this new position, then open the hand, etc. Okay, so by performing this sequence of action, so you can verify the robot will achieve this final assembly. Okay, so basically P2 is this one. Okay, move to P2, pick up the P2. Basically, first open the hand, go to P2, go to here, and then close the hand. Basically, to pick up the B part B. Then move to P1. P1 is on top of A. See, on top of A. Then open the hand. So basically, so this motion sequence will let the robot to pick up a part B, place it on top of part A. Okay. Then this one is go to position vector P3, to go to location of a part C, pick up the part C, and place it on top of part B. Okay. Then this one is go to part D and pick up the part D and place it on top of the sub-assembly at the location of part A. Because after this, at the P1, you have a B on top of A. After this, after execution of this sequence of motion, then you have a sub-assembly of C, part B, part A. Okay. Then after the execution of this motion sequence, then you will have D on top of sub-assembly of CBA. All right. So by executing this motion sequence, the robot will achieve this final assembly. All right. And here's an example of human-assisted motion planning for mobile robot. Okay, initial state is like this. Okay, robot is in room R1, robot is here. Box is in room R3, box is here. And there is a door between room 1, room 2. Room 1, room 2, you have a door D1. And this door between room 2, room 3. Okay, there's a door D2. Okay. Now we want the box to be inside room 1. Okay, this is the final state. Then what should be the motion sequence to be performed by the mobile robot? Okay, so you will see first, move the robot to room 2 through door D1. Okay, go to here. Then move the robot to room R3 through door D2. Okay, then push box back to room R2 through door D2. Then push the box to room R1 through the door D1. All right. Then by executing this motion sequence, then the robot will achieve this final result. Okay. Then come to this question. Okay, how to develop the script commands or library function. Okay, so the answer will be, so we have two versions of answer. Okay, one is to manually design by designer. Okay, so then the designer will come out these commands in script language, this library function in programming language. Okay, but in future we would like to achieve this result. Okay, let the robot to autonomously create the commands in script language and eventually use human language. Okay, so you see these are the commands which are very close to human language. Okay, and also let the robot to implement library function to create its own motion library function. All right, so these are the two scenarios. But in today's situation, so as a designer of a robot, so you must have a team, okay, with the focus on the manual development of these commands in script language and these library function, okay? Because when you want to sell your robot as a product to the buyer, so you must provide, okay, these script language and library function. Otherwise, the buyer of your product do not know what to do with your product, okay? If let's say your robot is not intelligent enough, then without this library function or without the commands, the buyer of your robot can do nothing. All right. So regardless how intelligent is the robot developed by you, try to provide, okay, the script language and the library function to the buyer of your robot. All right. Okay. Now come to this question: how to achieve autonomous motion planning by robot? All right. So then we can come out this term, okay, I call it as a level 1 or level 0 of robot intelligence, or intelligence readiness, level 0 of intelligence readiness, okay? So for today, most robots are at this level. So it means intelligence readiness of today's robot is 0 or level 0. Therefore, human operator must help the robot to undertake task planning, action planning, motion planning, path planning, trajectory planning, and send the motion function or equation to robot, then robot just execute, okay, your motion description in the form of library function or motion commands, okay? So this is the current situation in industry, all right? But however, in research area, we are able to reach this level. That means level 1 of robot intelligence or intelligence readiness at the level 1, okay? So this scenario corresponds to this situation. Today, we can send the motion description to robot. Let robot to autonomously undertake path planning, trajectory planning that we are going to study in the next 2 lectures, all right? Then perform the motion, okay? So therefore, we have this scenario, okay? So this is this scenario has already been achieved more than 10 years ago in research, in research lab or research institute, okay? And then what will be the future progress in robotic research? The future progress in robotic research should be to shift this module from human operator from human operator side to robot side. Let robot to handle this one and shift this one to here. So then robot will reach level 2 of robot intelligence or intelligence readiness at the level 2, okay? Then after that, we may also want to shift this one from human operator side to robot side, okay? Let robot to handle action planning. Then robot will reach level 3 of robot intelligence, okay? Then eventually we may shift this one from operator side to robot side. Then robot will reach level 4 of intelligence readiness, right? So you see, we still have a lot of progress to make in terms of robotic research, all right? Okay. So then the answer will be, if we want to achieve autonomous motion planning, the robot must at the least reach level 2 of intelligence readiness, okay? Then, however, for level 1 of intelligence readiness, it is not an issue. So you have seen this result, okay? So this is what we have done or what we have achieved in year 2000. So you see, it was 20 years ago, okay? All right. So in terms of hand-eye coordination, actually we have reached level 1 of intelligence readiness in year 1997 with industrial robot with robotic arm. And this video show you the result that we have done in year 2008.
To show you some demonstration. I am searching for object. Now I'm going to look at this position. Now I fire to object. I fire to touch target. I close fire. I fire to ready position.
Yeah. 把手伸过去，拖着手，
Right. So that's all for the study of lecture 3. So the key takeaway from lecture 3 is for you to understand the process of doing motion planning. So the input to the process is action description, and the output from motion planning is motion description in the form of script language or library function. And in addition, we have had a short discussion about the intelligence readiness of robot. And you understand that today's robot, most of them are at the level 0 of intelligence readiness. And in terms of research achievement, we have a solution for robot to reach level 1 of intelligence readiness. And of course, we need to continue to do research to increase the level of intelligence readiness. From motion description, then we will enter the study of path planning and trajectory planning, because we need to first transform motion description into equation of a motion, which could be understood by today's robot, which could be executed by today's robot. All right. So I'm looking forward to seeing you in lecture 4 of module 1.